So, welcome to the second example from chapter 12.3. Again we are going to solve the one dimensional heat equation. Now this time we are going to solve the heat equation which is given here. So, partial u over partial t equals to 3 times partial squared u over partial x squared, and my domain, let us say the length of the rod goes from 0 to 10. So, we have a rod, one dimensional rod, length of this rod is 10 and we have two boundary conditions. Again the temperature at the left boundary and the temperature at the right boundary equal to 0, and now we have an initial temperature profile that looks like this. So, here we have a piecewise defined function. So, this says from 0 to 5 on this, when t equals 0 on this rod the temperature equals to 3 up to x equals to 5, after that your temperature equals to 0. That is the initial temperature profile on this rod. Okay. Again, to solve this we use the same technique as before. So, in this video I may not do all the steps, I will do the key steps. The first step is to assume our u equals to big X of x times big T of t. In other words, we assumed our u can be expressed as a product of two functions. One function contains only the x variable and the other one contains only the t variable. And if you substitute this product into the differential equation, into the partial differential equation, you should get something like, say, x t dot equals to 3 times function t times x double dot. Now, if you take, let us say, the functions that are depend on t to one side, maybe you will get, let us say we divide both sides by 3tx. So, then we have t dot over 3t equals to x double dot over x. Okay. And now we use the same argument. In the left hand side I have a function that depends only on the t variable. In the right hand side I have a function that depends on the x variable, but our equation says this function of t equals to a function of x, and this happens only if this ratio equals to a constant, and let us say that constant equals to negative lambda. So, from this we can construct two ordinary differential equations. Your differential equation should be x double dot plus lambda x equals to 0, and then t dot plus 3 lambda t equals to 0. Okay. So, now we started with the partial differential equation. After this substitution, what we have is two ordinary differential equations. Of course, so this lambda can take three possibilities. Lambda can be 0, lambda can be a negative number, or lambda can be a positive number. Now, if you evaluate, so if you consider, let us say lambda equals 0, say lambda equals 0, and if you solve this first equation for big X of x, you should get, let us say, a1x plus b1. Okay. Now, if lambda is a negative number, let us say lambda equals to negative a squared, then big X of x equals to a2 times e to the ax plus b2 times e to the negative ax. in my first example I explained how to obtain these solutions. Now the third possibility is lambda can be a positive number. So, let us say lambda equals to a squared. In this case big X of x equals to a3 times cosine of ax plus b3 times sine of ax. Now, so the next step is to figure out these constants. Now, to do that we need to use the boundary conditions. Now, these two boundary conditions says the temperature value at the left end point equals to 0 and the temperature value at the right end point equals to 0. And since u equals to big X of x times big T of t, these two boundary conditions will give you another boundary conditions for big X of x. So, basically you should get big X at 0 equals to 0 and big X at right endpoint is at 10 equals to 0. Okay. Now, if we use these two boundary conditions to figure out the values of a's and b's, so for this particular case you should get a1 equals to 0 and b1 equals to 0. In other words, this big X of x equals to 0, which is the trivial solution. Even for the second case you should get a2 equals to b2 equals to 0. And now, as before we got the trivial solution. Okay. And this happens because of the homogeneous boundary conditions. Okay, so this is the interesting solution. Now let us try to find a3 and b3. If you evaluate this one at 0, you will get a3 times cosine 0 plus b3 times sine 0 equals to 0. Cosine 0 is 1, sine 0 is 0. So, basically this equation says a3 equals to 0. And next we are going to evaluate big X at 10, that is the right end point. Since a3 equals to 0, we are not going to get the first term, but we will get this. Therefore, we have b3 times sine of 10a equals to 0. 10a equals to 0. Now, remember we are looking for non-trivial solutions. So, in other words, b3 cannot be equal to 0. Since we have a product that equals to 0, this means the sine of 10a term should be 0. And we know that if this angle equals to this angle 10a equals to an integer multiple of pi, then we are going to get sine of 10a equals to 0. So, in other words, sine of n pi equals to 0. So, using this equation we can solve for a equals to n pi over 10. Great. So, if a equals to n pi over 10, then this equation is satisfied. Therefore, this solution will satisfy the given boundary conditions. Let us update our big X of x. We have b3 times sine of, instead of a I can write n pi over 10.
I need to stop you right quick.
Okay.
Rolling.
Okay. So, we found that if a equals to n pi over 10, then this equation is true, and with this a value our solution big X of x will satisfy both boundary conditions. So, now we can update our big X of x, which equals to b3 times sine of, instead of a I can write n pi over 10 times x. Now, this is the form of the solution for big X of x. Okay. So, the next step is to solve the second equation for big T. It is a first order ordinary differential equation with constant coefficients. So, now big T of t equals to, let us say, some constant C3 times e to the negative 3 lambda t. So, basically we have to take the negative of this coefficient. Since I have plus 3 lambda in the solution, it should be negative 3 lambda t. Okay. But what is the value of lambda? Okay. So, lambda equals to a squared, but okay. So, lambda equals to a squared, a equals to n pi over 10, therefore, lambda equals to n squared pi squared over 10 squared. With this lambda value, we have our final solution for big T. It equals to C3 times e to the negative 3 times n squared pi squared over 10 squared times t. Okay. Finally, we can construct our solution for u of x comma t equals to big X times big T. Okay. So, if you multiply these two solutions, you will get b3 times c3, which is a constant, let us say d. You have d times sine of n pi x over 10 times e to the negative 3 times n squared pi squared over 10 squared times t. Okay. Now, this solution depends on your integer n, but this solution satisfies both boundary conditions. So, at this point we have a family of solutions. To denote that family of solutions, I am going to write subscript n for u and subscript n for d. Right. For each n value, you will get different d value, therefore, a different solution. And here n goes from 1 to up to infinity. Okay. So, the final step is to figure out a value for d n using the initial condition, and that we are going to do next. Okay. Let us see.